The purpose of this video is to review some key trig identities, trig properties, special right triangles, important things that you need to know from trig in order to be successful in future classes, and in this sense to be successful in calculus. So this video by no means is a brand new tutorial on new content. It's a review and a refresher on some other content that you should have learned in previous classes. So a couple of things. Let's start with right triangle trigonometry. Right triangle trigonometry. And what I'm actually going to write in this middle circle is the acronym that is most commonly used to help us understand sine, cosine, and tangent. And that acronym is Sohcahtoa. And this acronym, Sohcahtoa, reminds us that if we have a right triangle and we are looking at some particular angle, theta, that sine is opposite over hypotenuse. So remember, opposite is the one that's across from the angle that we're looking at. If I was standing at the corner that makes that angle, I'd be looking at the opposite. The hypotenuse is always across from the right angle, and the adjacent is the side that's touching the angle. That's not the hypotenuse. So sine is opposite over hypotenuse. Opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent, and that comes from Sohcahtoa. Now, cosecant is the reciprocal of sine, so it's hypotenuse over opposite, aka it's 1 over sine of theta. Similarly, secant is the reciprocal of cosine, so it's hypotenuse over adjacent, aka it is 1 over cosine of theta. And cotangent is the reciprocal of tangent, so it's adjacent over opposite, or it's 1 over tangent of theta. So those are the six basic trig functions that we use here. The next thing that we want to talk about just briefly is special right triangles. So there are two special right triangles. One of them is a 45, 45, 90. And what makes this triangle special is that it's a right triangle, and if the angles are the same, that means the lengths of the side are the same. And you could use the Pythagorean Theorem to find the length of the hypotenuse, which would be x times the square root of 2. And if you don't believe me, you could do that out. X squared plus x squared equals c squared, or the hypotenuse squared. This would give us 2x squared equals c squared. And then to solve for c, the hypotenuse, we would square root both sides, which would give us the square root of 2 times the square root of x squared, or x times the square root of 2. But we're not proving why a 45, 45, 90 triangle is set up that way. We're just remembering what it is. So the legs are the same length, since the angles are the same, and the hypotenuse is the length of the leg times the square root of 2. The other type of special right triangle is a 30, 60, 90 right triangle. Remember, 30 degrees would be across from the shorter side, or opposite the shorter side. 60 degrees would be opposite the longer side. And the way that this special triangle works is that we can call the shorter side x, the hypotenuse would be 2 times x, and the longer side would have a length of x times the square root of 3. So there's lots of ways to use this information to find particular pieces. If you have the hypotenuse, you can use these relationships to find the shorter or longer leg. If you have the shorter or longer leg, you can use this information to find the other two pieces. So special right triangles are important. They come into play the most often in higher level classes when we think about the unit circle, which we're going to talk about a little bit later in this video. The next thing are some basic trig identities that you should know. The most common one is that sine squared plus cosine squared is equal to 1. If you know that one, I'm going to tell you a secret. You can come up with these two really easily, and let me show you how. If you take sine squared plus cosine squared equals 1, and that can be shown to be true in a variety of ways, but the purpose of this video isn't to prove these identities to you. That was the job of an earlier teacher in Algebra 2 or Pre-Calc. It's just to remind you how to use them. The way to do this is, let's go ahead and take this entire equation and divide it by sine squared of theta. Divided by sine squared of theta. The division property of equality says I can divide as long as I do it everywhere. Sine squared divided by sine squared is 1. Cosine squared divided by sine squared, well, cosine over sine, and actually let's go back. I'm going to add another identity over here. The other really essential identity to know is that tangent of theta is equal to sine of theta over cosine of theta, which means the reciprocal of this, cotangent of theta, would be cosine of theta over sine of theta. So going back here, I have cosine squared divided by sine squared. That's going to give me cotangent squared theta. And 1 divided by sine squared, well, what identity is 1 over sine? 1 over sine is cosecant, so this would be cosecant squared. So we are here. And yes, this bottom one is in terms of x. The order is slightly mixed up, but where does this come from? It comes from dividing the original one by sine squared theta. Now, similarly, if instead of dividing by sine squared theta, you divided by cosine squared theta, so let's say that I divided by cosine squared theta. Sine squared divided by cosine squared would be tangent squared theta. Cosine squared divided by cosine squared would be 1. 1 divided by cosine squared. 1 over cosine is secant, so this would be secant squared theta. And that gets us this one. So if you know, the moral of the story, if you know sine squared plus cosine squared equals 1, and you're having trouble remembering the other two, divide by sine squared, that'll give you one of them. Divide by cosine squared, that'll give you the other. Also, the big one not to forget is that tangent of theta is sine over cosine. Again, I would love to go into the proofs of these. That'll happen in a different video, not for this particular course, since that is old news, I hope. The last thing we're going to talk about before we get into some examples are quadrant signs and ratios, and also angles to points in the plane. So one thing that I want to remind you is that if we have a point in an xy plane, that point could create a triangle with the origin, and that angle would be our theta, which means we could talk about our opposite being our y value and our adjacent being our x value. And then if we know the coordinates of this particular point, like if this point was, let's say, 3, 1, we could use the Pythagorean Theorem to find this side length, which I'm going to call r. And if we know all those side lengths, for example, sine of theta, in this case, that would be y over r, opposite over hypotenuse. Cosine of theta, that would be adjacent over hypotenuse. Tangent of theta, that would be opposite over adjacent, and all of their reciprocals as well. So if you have an ordered pair, that's really helping you identify what your x and y value are so that you can calculate any of these particular things. And then signs, an acronym that's commonly known is that all students take calculus. In this quadrant, everything is positive. Sine, cosine, tangent, cotangent, all their inverses. If you have a point in the first quadrant, all of them are positive. If you have a point in the second tangent, sine is the only one that's positive. If you have a point in the third tangent, in the third quadrant, tangent is the only one that is positive. And if you have an ordered pair in the fourth quadrant, cosine is the only one that is positive. So let's take some of this refresher and work through some examples. First thing we're going to do is verify a trig identity, or prove that the quantity 1 plus cosine theta times the quantity 1 minus cosine theta is equal to sine squared of theta. So when we're doing this, we're not manipulating both sides of the equation. We're really trying to work with the left-hand side to eventually simplify it down so that we can show that this is true. So I need to work with this and manipulate it to get it down to be sine squared. So my first thought is I can't do anything with just cosine of theta, but I could do something if I had cosine squared. So what I'm going to do is I'm actually going to distribute here. This is the difference of squares, but in case you don't see that, I would have 1 minus cosine of theta plus cosine of theta minus cosine squared theta, and then minus cosine theta plus cosine theta, that's going to add to be 0. So I have 1 minus cosine squared theta. Well, we know that 1 is the same thing as sine squared theta plus cosine squared theta. And then I'm going to just bring down this purple cosine squared theta that was already there. And if I combine negative cosine squared and positive cosine squared, I get 0. So what I'm left with is sine squared of theta, which does in fact equal what we were trying to verify. So remember that when you're manipulating and verifying, that your goal is to make it turn into something else. And the way that this type of thing gets used in calculus a lot is in a more straightforward way, trying to go from a function that we may not know how to deal with into a function that's easier to deal with. And you'll see that when we start getting into the calculus of things in future units. Let's look at some more examples. All right, these 3 examples are asking us to determine the 6 trig functions using the given information. So our ultimate goal for number 1, since we have sine, is to find cosine of theta and tangent of theta, and also to find their inverses. And I always like to write these side by side. So the inverse of sine is cosecant. So I'm going to go ahead and write cosecant of theta here. The inverse of cosine is secant. The inverse of tangent is cotangent. We're going to find each of those values. Well, if we're given sine, all we have to do to find cosecant is flip that over, take the reciprocal. So cosecant of theta will be 13 over 11. Now, how do we find the rest? Well, this is right triangle trigonometry, so let's just draw a generic triangle. I'm going to call this angle theta. If sine is 11 over 13, that means 11 is opposite and 13 is hypotenuse. 11 is opposite and 13 is hypotenuse, which means I can find this missing side by using the Pythagorean Theorem. 13 squared equals x squared plus 11 squared. 169 equals x squared plus 121. X squared is 48. X is going to equal the square root of 48, which could be simplified if you needed to simplify that. The square root of 48 is the same thing as the square root of 16 times the square root of 3, or 4 root 3. Now, in higher level math classes like calculus, you really don't have to worry too much about simplifying radicals like this, and you definitely don't need to worry about rationalizing the denominators. But now we know what this last side is, so let's go ahead and clean this up a little. Okay, so the cosine is going to be adjacent, which we just figured out is 4 times the square root of 3, over the hypotenuse, which is 13. Let's move tangent down a little bit. Tangent of theta is going to be opposite. Opposite is 11 over adjacent, which we just figured out is 4 times the square root of 3. Now, in other classes, you would likely have to rationalize that. In this case, I am fine with you leaving it unsimplified. Cosine and secant go together, so I'm going to take the reciprocal here, 13 over 4 root 3, and cotangent would be 4 root 3 over 11. So there are my 6 trig functions. Now on number 2, instead of being given a trig function to start with, we don't have sine or cosine or tangent, we have a right triangle. This is a Pythagorean triple. 3, 4 makes the hypotenuse 5. If you did not know that, you would just set up the Pythagorean theorem and solve for c, and you would get 5 in that way. So sine of theta, which I should have indicated for you, we're going to call this theta. Sine of theta is going to be 3 over 5, opposite over hypotenuse, which means that cosecant of theta is 5 over 3. Cosine of theta is going to be adjacent, 4 over hypotenuse 5, which means that secant of theta is going to be 5 over 4. Tangent of theta, opposite over adjacent, 3 over 4, so cotangent of theta, 4 over 3. Now I'm going to encourage you to pause the video and see if you can work through number 3 on your own. Remember, like on number 1, you can draw the triangle, you can identify the reciprocal trig function or the inverse trig function right away. So hopefully you have had time to work on this. If cotangent of theta is 1 over the square root of 3, then tangent of theta is the square root of 3 over 1, since they are reciprocals. Let's go ahead and create a triangle. I'm going to call this theta. Cotangent is adjacent over opposite. So adjacent is 1 and opposite is the square root of 3. And we can find the hypotenuse using the Pythagorean Theorem. And that's going to give me that C is 2. So sine of theta, opposite, root 3 over 2, which means that cosecant of theta is 2 over root 3, and I don't need you to rationalize there. We haven't found cosine yet, which is going to be 1 over 2, which means that secant of theta is going to be 2 over 1, or just 2. Now let's build on what we were talking about earlier with special right triangles and extend that idea to the unit circle, probably one of the most foundational pieces of trig that you need in this class. The unit circle is hopefully something that you spent a good amount of time coming up with, memorizing, and learning how to work with in previous classes. Briefly, I will just mention that the unit circle comes from creating special right triangles on the unit circle, and the unit circle has a radius of 1. So this angle here would be a 30-degree angle, and based on special right triangles, that would make the opposite side be half of the hypotenuse. If the hypotenuse is 1, then this is 1/2. And the adjacent side would be the shorter side 1/2 times the square root of 3, which would give us the square root of 3 over 2, which are the coordinates to this ordered pair here. Not a coincidence, that's how this works. Similarly, if instead of making the 30-degree angle, I made the 60-degree angle, still a right triangle. This is now 60 degrees. The hypotenuse is still 1. Now those two sides are just going to flip. This would be 1/2, and this would be root 3 over 2. And then lastly, the 45, 45, 90 triangle would come in here. This is 45 degrees, which means that the legs are the same length and the hypotenuse is 1. So you could think of that as 1 equals any side times the square root of 2. So x equals 1 over the square root of 2, which if you rationalize, which in the unit circle it is rationalized typically, you see the square root of 2 over 2, which is why both x and y are the square root of 2 over 2. That's where the ordered pairs come from. A couple of other things to remember: the ordered pair, every ordered pair in the unit circle, not every ordered pair that you consider, but every ordered pair in the unit circle is of the form cosine theta, comma, sine theta. For the same purpose that we just created this, you could make that triangle. You don't have to come up with each angle. So if I asked you what the cosine of 30 degrees is, you should be able to tell me, well, that's the x coordinate. That's root 3 over 2. Similarly, if I asked you for the sine of 60 degrees, you should be able to tell me that that is root 3 over 2, the second coordinate. Now, the radians fall in there as well, and I'm hoping if you're at this level of math that you already are feeling comfortable with radians. If not, check out a video and get yourself filled in there. So find the exact value, the sine of pi over 3. So that means we're thinking about this coordinate. Sine is the second point, or the y value. The y value of that coordinate is root 3 over 2. Tangent of 7 pi over 4. So what you need to do is figure out where that ordered pair is on the unit circle, this one here. Tangent is the same thing as sine over cosine, which means I can take the sine value, which is the y value, negative root 2 over 2, and I can divide that by the cosine value, root 2 over 2. And this is going to give me negative 1. So tangent of 7 pi over 4 is negative 1. Go ahead and pause the video and work through cosine of 5 pi over 6 and cosecant of pi over 2. Well, here's the ordered pair for cosine of 5 pi over 6, and the cosine is going to be the x value, which is negative root 3 over 2. Similarly, Cosecant of pi over 2 is on the axes. Cosecant is the same thing as 1 over sine, in this case, of pi over 2. And sine, in this case, is 1, so that's going to be 1 over 1, which is just 1. So hopefully that was a great little refresher. Let's look at a few more examples tying these concepts together, and then we'll wrap up this video. So what I'm going to encourage you to do here is to pause the video and work through these 4 examples on your own. Some of them you're going to get stuck on, but your goal is to find the 6 trig functions. And if you get stuck, you can unpause the video and watch me work through them. But hopefully you can pause the video and get through some of them. Okay, a triangle through the point 2, -2, 3. So let's plot that point. -2, 1, 2, 3. That would be here. So I'm creating this right triangle. This length is -2. This length is 3. How do we find the hypotenuse? We do the Pythagorean Theorem. So 2 squared plus 3 squared is going to be 13. So this is going to be square root 13. So sine of theta, which is going to be this angle here, is opposite, which is 3, over hypotenuse, which is the square root of 13. Which means that cosecant of theta is the square root of 13 over 3. Now, in this quadrant, both of those values are positive. Sine, all students, right? This is the students' quadrant, so sine and cosecant should be positive. Let's look at cosine now. Cosine of theta is adjacent, which is -2, over hypotenuse, which is the square root of 13. It should make sense that cosine is negative, since in this quadrant, quadrant 2, cosine should be negative. So secant of theta would be negative square root 13 over 2, or you can leave the negative sign with the 2 in the denominator. And last but not least, tangent of theta, opposite, which is 3, over adjacent, which is -2, meaning that cotangent of theta is -2 over 3, or 2 over -3. So here's my clue to you on number 5 if you were stuck. If sine of theta is -3/4 and we're in quadrant 4, that makes this 3 positive and this 4 negative. Now see if you can use the same techniques that we use in number 4 to find the 6 trig functions. So hopefully you figured out that the hypotenuse is 5, that sine of theta is going to be, well, we already know what sine of theta is. It was given to us. That means that cosecant of theta is -4/3. Cosine of theta, this is our positive, is 3 over 5, adjacent over hypotenuse. This is our, all students take calculus, our 4th quadrant, so cosine and secant should be positive. And then last but not least, tangent of theta should be opposite over adjacent, which means cotangent of theta should be adjacent over opposite. Here's my hint to you on number 6. This is telling you a specific point on the unit circle. That point is 0, 1. So sine of theta is the y value. Sine of theta is 1. Cosine of theta is 0. Tangent is sine over cosine, which is 1 over 0. That doesn't make any sense. So tangent of theta is undefined because I can't have 1 over 0. Cosecant of theta, the reciprocal of 1 is 1. Secant of theta is the reciprocal of cosine. That's going to be undefined also because I can't take the reciprocal of 0. Cotangent, the reciprocal of 1 over 0 would be 0 over 1. I can take that reciprocal. That's just going to be 0. So for number 7, the line y equals 3/4 x, but in quadrant 3, well, y equals 3/4 x has a y-intercept of 0. Normally we would go up 3 and over 4, but we need to go backwards, so down 3 and right 4. So here is the triangle that I'm creating, and we always create the triangle with the x-axis. So we can find lengths here. This is -3, and this is +4. This is a 3, 4, 5 triangle. So I'm just going to put the answers in here for the 6 trig functions. I think it's pretty straightforward after that. So here we have those 6 trig functions. So go ahead and pause the video and make sure you got them correct. Let's recap what we learned in this lesson. We reviewed Sohcahtoa, the 6 trig functions, and how to find them given a triangle. We talked about how to plot a point so that we could create a triangle to find those same 6 trig functions. We talked about which ones are positive in which quadrants. All students take calculus, all being quadrant 1, students being quadrant 2, tangent being quadrant 3, cosine being quadrant 4. We talked about the basic trig identities that you should know and be able to work with. And we talked about special right triangles. We then extended those ideas to the unit circle, talked about how every ordered pair on the unit circle is cosine comma sine, and how we could find exact values, whether in radians or degrees, using the unit circle. And then we did just some more practice with all 6 of those trig functions. So hopefully you're getting really comfortable, you're getting a little refresher of things you may have forgotten about, and you are feeling more confident. So go ahead and write down any questions you have or post them below, and I look forward to supporting you on this. Thank you for listening.